Hello and welcome to Mathematics with Simon. I'm Simon. And that's Chewy. Just yesterday I was just wondering how to prove Pythagoras' theorem, and often when we do a lot of advanced mathematics, it's sometimes good to check back. We can prove the basic theorems. Pythagoras' theorem is a pretty basic, wonderful, useful theorem that you use in all sorts of ways. You use it in basic geometry, you use it in metric space theory, you use it all over the place. But I just thought, actually, how do we know it's true? How do we prove it? And this is one of the most useful questions in mathematics. So, given a right angle, the question of how do we know, how can we prove something, is one of the most useful questions in mathematics. It's at the heart of mathematics, the concept of proof. So, proof basically means that you use logical steps and you start from things you know to be true. That's a bit controversial. You start from things you know or assume to be true, and then you get to the result that you want to establish. So here's a triangle, a right angle triangle. We're going to call the sides A, B and C in length. The one opposite the right angle we're going to call C. That's the longest side, sometimes called the hypotenuse. Pythagoras' theorem says that a squared plus b squared equals c squared. So just some examples. If the sides were 3, 4 and 5 in length, this would work. This would be a right angle triangle because 3 squared plus 4 squared equals 5 squared. In other words, 9 plus 16 is 25. Also, if the sides were 5, 12 and 13 in length, 5 squared plus 12 squared equals 13 squared. 25 plus 144 equals 169. These are called Pythagorean triplets. When you have three whole numbers that can be the sides of a right angle triangle, they're called Pythagorean triplets. There is an infinite number of them. I suppose the next thing I'm wondering is how you work them out. There'll be a way. You can sort of guess them, but there's probably a system for working them out. Now that's interesting me. Anyway, we'll go on to that in the future, next video, or another video. Right, how do we prove Pythagoras' theorem? So, a squared plus b squared equals c squared. How do we prove this? By the way, since I'm going to talk about Pythagorean triplets, it's particularly significant because, of course, if these were cubes or fourth powers, there are no numbers that satisfy those equations. That's Fermat's last theorem, which took years and years and years to prove, and was only proved very recently by Andrew Wiles, who's now at Oxford University, who has a big building named after him. So the idea of whole numbers that satisfy these equations is quite important because it comes in really, really advanced maths. Okay. So how are we going to prove this theorem? Well, and there's an interesting thing here, isn't there, by the way, which is that geometry and algebra are connecting. So we're working in geometry, but actually now this is linking to big problems in algebra, because Fermat's last theorem is basically an algebraic problem. Anyway, how do we prove it? Well, here's what I've done. Firstly, I've taken a triangle ABC and I've called the angles theta and phi. Now there's no need to worry about what these are called. They can be called anything, but theta and phi are good names because we often label an angle with theta or with phi. Then what I've done is dropped a perpendicular. So I've drawn a line from the vertex B to the hypotenuse, and it's a perpendicular. So there's two right angles on either side where it meets the hypotenuse. And then we can do a bit of thinking, because basically for the triangle ABD, we know that this angle's theta, this is a right angle, so this must be phi, because phi equals 90 minus theta. We know that from the big triangle, that phi equals 90 minus theta. So this must be phi. Then this is 90. So because phi equals 90 minus theta, theta equals 90 minus phi, so this must be theta. And when we look at what we have here, we have three triangles. We realise they're all similar triangles. So the big triangle ABC is similar to ABD, is similar to BCD. Now, what do we mean by similar? What we mean is they're basically the same triangle, but they're coming in different sizes. So ABC has a right angle, theta and phi, and then ABD has a right angle, theta and phi, and then BCD has a right angle, theta and phi. So they're the same shape, they're just coming in different sizes. And because there are similar triangles, there are some things that we know. So we know that the ratio BC over AC. So what we're going to take is, we're going to take the side opposite theta and divide by the hypotenuse in the big triangle. So in ABC, we're going to take the side opposite theta, BC, divide by the hypotenuse, which is AC, and that ratio is the same for the smaller triangles. So for the triangle BCD, we're going to take the side opposite theta, which is CD, and then divide by the hypotenuse, BC. And then for the smaller triangle, we're going to take the side opposite theta, which is BD, and divide by the hypotenuse, which is AB. So BC over AC equals CD over BC equals BD over AB. And actually they all equal, as it happens, they all equal sine theta. And in a similar way, we can look at the side opposite phi and divide by the hypotenuse. So AB over AC. AB is the side opposite phi in the big triangle ABC. AB over AC equals BD over BC equals AD over AB. So AD is opposite phi in the small triangle ABD. And AB is the hypotenuse. So we know that all these ratios are equal. We can then do a bit of simple sort of algebraic manipulation on this. So if we multiply both sides by BC and by AC, this tells us that BC squared equals AC CD. We're multiplying both sides of this by BC and then both sides by AC. If we multiply both sides of this by AB and AC, we know that AB squared equals AC AD. So this is hopeful because BC squared is this short side of the big triangle. AB squared is this short side of the big triangle. Then we're going to add these two together, AB squared plus BC squared. AB squared plus BC squared equals, and what we can see from the previous page is, it equals ACCD plus ACAD. So it equals ACAD plus ACCD, and then we can take out AC as a common factor. We're just left with AD plus CD. Now AD is that bit, CD is that bit. Add them together, we get another AC. So AB squared plus BC squared equals AC squared. That is the answer. That is Pythagoras' theorem proved. So we've basically proved it using the ideas of similar triangles, which is really nice. There are other proofs. Maybe sometime we'll do another proof. I hope you've enjoyed this quick video. If you have, please hit like. If you want to see more, please hit subscribe and the notification bell. Hope you enjoy maths and send me your problems. So few people have sent me problems now, which I'm doing, and I think that's really fun. So if there's something you'd like me to look at, just write it as a comment, or I don't know, find some other way to send it to me, and I'll look at it for you. I hope you're all well, and Chewy and I really look forward to seeing you next time. I'm going to take him for a walk now. Bye bye.